Here we go. So this is going to be, what's today, 2/18? Five 5.6. Graphing. Linear inequalities in two variables. Graphing linear equations in two variables. We are just going to jump right in with some examples. And this is exactly what we kind of did in our warm-up. So here is our inequality. 2x plus y is less than -3, and I have the ordered pair, -1, 9, and I want to know, is it a solution? What in the world do you think you're going to do? You're going to substitute it in. I have an x. I have a y. Substitute those in. 2 times x, but x is -1 plus y, which is 9, is less than -3. That would be -2 plus 9 is less than -3. 7 less than -3. That is false. And then I would say, there's my symbol for therefore again. The ordered pair, -1, 9, is not a solution. It's not a solution because I get a false statement when I plug it in. (5x minus 2y) is less than or equal to -1, and I want to know, is the ordered pair for -1 a solution? Take about 30 seconds, see what you get. I'm going to do it as well. Hopefully you got what I did. I substituted that -4 in, got -20 plus 2, -18 less than or equal to -1. -18 is less than or equal to -1. It's true. Therefore, that is a solution. Satisfies the inequality. You guys remember doing these? Somewhat? When we were solving inequalities, right? Compound inequalities. We had and statements, or statements. They were on the number line. And this is taking them, putting them in a coordinate plane. The nuts and bolts, though, is going to be the graphing. And that's what we're doing next. So this is graphing. And this is what the next two sections are going to be. And there's definitely some steps. You are going to graph the inequality. Y is less than or equal to 2x. With this, we're going to talk about getting our boundary. In the boundary to the solution set of these inequalities is going to be this line. I'm going to call that getting the boundary. But really what we're going to do, the boundary is the line. Get your boundary. And we do that by making it look like y equals mx plus b, because the boundary is going to be a line. Does that look like y equals mx plus b? Certainly does. Remember, when I'm solving these, I treat this just like an equal sign, right? I move back and forth over the inequality just like it's an equal sign. So this is just like y is equal to 2x, right? Which means I would have a slope of 2 and a b of what? 0, because there's nothing off here. And you can certainly write that as 2 over 1. I take this inequality, I make it an equation so I can identify my slope and y-intercept. The next thing we got to do is consider that symbol right there. Yes, but we got to add one more thing. If you have less than or equal to, or you are greater than or equal to, your boundary line is going to be solid. And this should be a little intuitive going back to graphing these on a number line, right? If it was less than or equal to or greater than or equal to, and I'm on a number line, was that an open or closed circle? It was a closed circle. When we were doing piecewise functions, if it was greater than or equal to or less than or equal to, that point on the boundary line was closed. It's the same concept here. When you have this less than or equal to, you have a solid boundary line. So on the flip side of that, if you have less than or greater than, that is going to be a dashed line or a broken line, however you want to say it. That is going to be key. Now I'm ready to graph, and I'm going to make a little XY coordinate plane. Well, I just got to go through 0 with a slope of 2, right? So it doesn't need to be terribly big on this one. So I'm going to make my x-axis and my y. I have a y-intercept of 0, goes through the origin, and I have a slope that's positive 2, meaning my line is going to rise, and I am going up 2 and over 1. Up 2 and over 1. And I certainly can take this down 2 to the left 1 in the other direction. There's my boundary. I've got to put my line in. It is less than or equal to, so is it going to be solid or dashed? It is going to be solid because that is a less than or equal to, and I know I need a solid line. I can pencil in that solid line next. There's my boundary line. And now, here's where the inequality comes in. We are going to have to shade, because not everything is going to make this true, right? Not everything on here is a solution. Before, when we were checking for solutions, we were finding points that lie on the line, and then we'd plug them in. Now I have a sort of solution set. All y's that are less than 2x. You want y's that are getting smaller. Where are y's going to be smaller? Above this line or below this line? It's going to be this side of the line.
So we shade that side.
Yes. The side of this line, that's the solution set, is everything to the right of this line. How did I know that it was everything to the right of this line? Because I want y's that are less than. I want y's that are getting smaller. Where are y's getting smaller? Down here, which means that has to be included in my shading. You don't have to do it that way. You can always test a point. And I test a point either to the right or to the left of this line, because I know my shading is either going to be above the line or below the line, because I only have one of them. What's an easy point to test on this one? I think it's this point right here. What is that ordered pair? 1, 1, isn't it? I could choose any point that lies in this shaded area, but I'm going to choose 1, 1 because it's easy to work with. This is where the plugging it in and seeing, is it a solution? Because if I get a true statement with 1, 1, that means it's going to be included in my solution, means that's where my shading is going to be. Well, test, I'm going to say test 1, 1. You have an x, you have a y. Your inequality, y is less than 2x, y would be 1. Is 1 less than or equal to 2? It is. So I would want to include this point in my shading, and that's why I got shading there. Now, if I chose to choose the point -1, +1, x of -1, so let's just say that. Let me put that there. -1, 1. If I tested that point, and I have y is less than or equal to 2x, 1 less than or equal to -2. Is that true or false? Is 1 less than or equal to -2? No, it's false. That's why there's no shading included in that point. Do you see that? We include true statements. Everything that's to the right of this line, any ordered pair you choose, will satisfy this inequality. Anything that's on the left ordered pair would not satisfy it. That's where the shading comes in. You picking it up? Let's do another one. Graph. -x plus 2y is greater than 2. I'm going to follow the same steps every time. I got to get my boundary. I want this to look like y equals mx plus b. As it sits, does it look like y equals mx plus b? No, it does not. I need to solve this for y. What would I do to solve it for y? Add x and then divide everything by what? 2. Add x. That goes away. 2y then is greater than x plus 2. I then would divide everything by 2. Y then is greater than x over 2. What is x over 2? What's my slope then? 1/2. Very good. Dividing by 2 is like multiplying by 1/2. So this is 1/2 x plus 2 divided by 2 is 1. That's what I want to graph. I have now a slope of 1/2 and a b, or a y-intercept, of 1. You are going to have a dashed line with a slope of 1/2 and a y-intercept of 1. Let's graph it. Here's my x, here's my y. I have a b of 1 or a y-intercept of 1. It's got positive slope, so I know it's going to rise. I leave my pencil on that y-intercept, a rise of 1, a run of 2. A rise of 1, a run of 2. And I can certainly take that in the other direction, going down 1, to the left 2, down 1, to the left 2. I think I've got plenty of points there. Now when I go into drawing my boundary, I go back to my inequality statement. Solid or dashed line? Dashed because it is not equal to. Don't put a solid. And a lot of times, students that have trouble I'm not going to guess whether you're putting in, oh, Mr. DeLong, that is a solid line. Well, you know what? You got to make it solid. You got to make it dashed. People that have trouble doing this, they'll just make a solid line and then they might go back and erase it, right? Put dashes in that way if you forget. Make it so I can tell. That's the bottom line. There's my line. Now, I can test a point that's not on the line. And before, I tested the point 1, 1 because it's easy. But I didn't test the point 0, 0. And I didn't test the point 0, 0 back on this one because it went through the origin and it lied on the line. You want to choose a point that is not on the line. So in this case, I'm going to choose to test the point 0, 0. Why? Because it's not on the line and it's really easy. Look at how easy it is to test this. I'm going to test that point right there, which is 0, 0. And I'm going to go back to my original inequality. Negative x plus 2y is greater than 2. Look at how easy this becomes to test. 0 in for x, 0 in for y. So what do I have on my left? 0. This is not 0 here. Sorry, that's a 2 for my original inequality. 0 for x, 0 for y. So I have 0 on the left. 0 greater than 2. That's false. And I'm going to say, therefore, 0, 0 is not included in the solution set. It's not included in the solution set. So if I test this and I get a false statement, do I want to shade there? No. No. I want to shade away from that point. I want to shade everything that's right here. And again, if I look back on my inequality here, and especially when I solve for y, look what this says. Y's are greater. Where are y's getting bigger? Above this line or below it? They're getting above it, right? So you can shade that way, or you can test a point. You're going to want to test points when we get into systems for sure. But I can certainly do this either way. Even when I do systems, I'm going to look at these and say, hey, I want y's that are greater. That's above the line. That's where y's are getting bigger. I tested this point 0, 0 because it was easy. I got a false statement, which means you certainly don't want to include that. I shade away. Picking up what we're doing? Okay, here's a couple. And these come up quite a bit. We are going to graph 2. Y is greater than -1, and you are going to graph also x is less than or equal to -4. I am going to make 2 coordinate planes. What's the line y equals -1 look like? Going old school graphing. What's the line y equals -1 look like? How do I graph that? Horizontal line going through what? -1 on the y-axis. Horizontal line going through -1 on the y-axis. Solid or dashed? Dashed because it's equal to. So you've got this line that passes through -1 on the y-axis. And now I can either test a point or I can just use my brain. Where are y's bigger than -1, above or below the line? Above the line. Or if you tested the point 0, 0, your y would be 0. Is 0 greater than -1? It is, which means you'd want to include it in your shading as part of the solution set. And I shade everything above. And again, back to why we shade. Any value of y that is above this dashed line when plugged in to my inequality gives me a true statement. What's the line x is equal to -4 look like? It is a vertical line going through -4 on the x-axis. 1, 2, 3, 4. Solid or dashed line? Solid. 1, 2, 3, 4. It's going to be a solid line going right through there on my x-axis. And now I can either test a point or use my brain. Where are y's less than where are x's less than -4? To the left or to the right of that line? They are to the left. That's where x is getting smaller. Or if you tested 0, 0. Is 0 less than -4? 0 is not less than -4. I would not want to include the origin in my shading, and that is why I shade everything to the right of, to the left of that line. That is it. That is 5.6 graphing linear inequalities.